Alright, given two strings, S and part. Given two strings S and part, perform the following operation on S until all occurrences of the substring part are removed. All occurrences of this are removed. And I'm sure, yep, A, B, C, A, B, C, dab, yep. Okay, I'm thinking of recursively iterating on this string and then removing every instance of ABC that I find, and then returning the remainder of the string as I recursively iterate. So it'll be easier to dynamically check the occurrence of part in the string as the string continually shrinks in size. Yeah. So I'm gonna return remove S part, and then probably an index, public void, string remove. We're gonna have an integer of index, a string S, and string part. Actually, I don't know how. You could do, like, the naive approach would be to do while s dot contains part, and do s dot index of part for I equals s dot index of part, and then I has to be less than part, or start equals s dot index of part, and then in I equals start, I has to be equals start, I has to be less than start plus part dot length, I plus plus s equals s dot substring. Oh wait, yeah, it's s equals s dot substring 0 start plus s dot substring start plus part dot length. Yeah, and then return s. Oh yeah, this will pass because s's constraints are so low. This is not very indicative. Yeah, there's got to be a faster way to do this though. Or not. This is a medium? Brother. This is really the fastest way because this is O of n. This is O of n. So this is O of n squared. Is the fastest really O of n squared? Oh, wait. This is O of n, but we don't run this O of n time. So this is actually O of n, the entirety of this. Because the check is just O of n. But this is O of m, where m is the amount of parts. So this is actually quite efficient. Oh, never mind. Knuth-Morris algorithm? Knuth-Morris CAMP, bro. I hate this CAMP. I've seen CAMP like 20 times. What does KP run in? O of n plus m. This is way faster. Is this really O of n times m? Because we don't run the while loop s times. We run it based off of this condition. So this condition runs, and then this condition runs. This condition doesn't run as many times as this condition runs. That's why I'm very what's SGPT? I guess. That wasn't very valuable. Oh, nice. What does generate image do? Oh. What does that show as? Oh, wow. Yeah, this heat map is atrocious. So here, what we're gonna do is we're gonna track a rolling minimum and a rolling maximum of the values that we have already encountered, and we're gonna iterate through the numbers array, obviously. And whenever we encounter a negative number, we are going to flip the minimum and maximum and then multiply by the upcoming number. And throughout that process, we're going to keep track of a maximum value an output value to be able to hold the maximum. So here I'm going to have int min equals integer dot max value, and then int max equals integer dot min value. And for every number in the nums array, if the number is less than 0, so if it's a negative number, I'm going to create temp1 or temp min equals min, and then a temp max value. Temp max equals max, and I'm going to swap min and max. And then I'm going to say the minimum is going to be equal to the minimum between itself and the minimum between itself, the next number, times the next number, or the next number itself. And we're going to do the same thing for the max, except for the opposite. So I'm going to calculate the max between itself, the itself times the new number, or the new number by itself. And then I'm going to return an output variable that I will declare and initialize here. So in output equals 0, and then I'm going to say output equals the max between itself and the max value. And if you run that, never mind. Are these okay as 0 then? It might be. This might be interfering with it. Oh, this is adding. Sorry, it's plus. Wait, what is going on? I'm kind of confused. 3. Wait. Biggest between -2, -1, and 1 is 1. No. 1 and -3, no. I don't remember how to do this. This makes sense. Whoa, what the? Interesting. That actually makes so much sense. We don't have to do the max because output will just take care of individual numbers. Oh my gosh. So Okay, there's some system design stuff that I want to go for. I can delete this. Oh my gosh, stop using O1. I got so tired of doing that. Okay. So we're going to make an output list, and we're going to backtrack on this array. We're going to backtrack on that array, keeping track of an index and adding and removing, or going into different paths of adding and removing. Basically, if we think about this as like a tree, in any given area, at like the root of a node, how do I describe this? So if we have something like the root of a node, each given root will have two children. So we either wait. Yeah, we either include or exclude a number, and this will keep on continuing. So here, here, I don't want to mess this up, but we will also include or exclude, and we will do the same here. We're going to include or exclude. Yeah, something like that. And because of this, we can just keep on including until we hit the depth of the recursion tree, the decision tree. So I can make a list of subset, or like an output list called subsets. That is a two-dimensional array list, and then I can backtrack on the numbers array. I will pass an index in, the numbers array in, and a subset array and the output array. And then I can return the subsets array. I will make the backtrack method where I have the index, the numbers array, a subset array, and a subsets array. For my base case, if the index equals the length of the numbers array, I'm going to take the subsets array and add a new array list with the values of the subset. And the reason why I do this is because the reference value for the subset will stay the same. So if I just add if I just did something like subsets.add subset, it will all the arrays will be the same because it'll point to the same reference, which is not what we want. We want to create we want to create a duplicate of it with a different reference. Otherwise, what we will do is we will follow the decision tree. So we are going to take the subset and add the current number, and then we're going to backtrack. We're going to say, okay, we're going to increment the index by 1, pass in the numbers, pass in the subset with a new value, and then pass in the subsets. And then after that, we're going to remove that value by saying subset.remove subset.size -1, and then we're going to backtrack one more time with the index incremented, but with the value now removed. And if we do this, we will get our What? Oh. Yep, and then the time complexity of this is going to be n to the power of 2, or no, sorry, 2 to the power of n, and the space complexity will be the same. Yep. Okay. So for this, we have a decision tree essentially, where for each value, we can either choose to include it or choose to include the next value. We can choose to include this or choose to include the next value, and then we can choose to include this or include the next value. And then you can go on and on until the array is, we've exhausted all the options in the array. And it says we can use the candidates, an unlimited number of time. So what I will do is I'll backtrack and I will recursively either decide to use the current number or the next number. The current number or the next number, and I'll keep on going until I reach the end of the array. And then if the value adds up to the target, then I will add it to an array which I will add to the output. So I have a list. I have a two-dimensional list, or I have a list of lists here, and I will call this output. I'm going to make it a new array list, and then I'm going to backtrack with an index variable, the candidates that I'm passing in, sorry, the target, and then the candidates that I'm passing in, and then a combination array and the output array, and then I'm going to return the output. I will now make the backtracking method where I have the index, the target, the candidates, the combination, and the output array. If the target equals 0, I'm going to take the combination, or sorry, the output array, and add a new array list of the combination. Otherwise, if the index equals the length of the candidates, or target is less than 0, I'm going to just return and suspend execution, and then otherwise then we start the backtracking. So we want to take the combination and add the current number, so candidates index, and then we want to backtrack. We want to backtrack with index, the same index, the target minus the candidates, or the current value that we've iterated through, the candidates, of course, the combination array, and the output. And then, after we backtrack, we want to remove that combination size minus 1. And then we want to backtrack with an incremented index and with the original target. And yeah, that should work. Okay, time complexity is O of 2 to the n, and then space complexity is the same thing because of the stack depth, and yeah. All right. So this is avoiding duplicates. So what we're going to do is we're going to do the same thing, but we're going to sort the candidates array to avoid duplicates. We're going to make the output array, and then we're going to backtrack with the index, target, candidates array, combination array, and the output array, and we return the output. We have the index here, target, candidates, combinations, output. If the index equals 0, or sorry, target equals 0, we're going to take the combination, the output, and add a new array list that has the values of the combination. Otherwise, if index equals the length of the candidates that we have, or target is less than 0, we're going to return and suspend execution. Otherwise, we're going to iterate throughout the candidates. If I equals index or candidates I does not equal candidates dot I minus 1. So if we are at the index that we're supposed to be at, or if it's not a duplicate, we can backtrack. So we're going to take the combination and add the current number, which is candidates I, and then we're going to backtrack with the current value of I plus 1, and then the target minus the current value, and then the combination array and the output array. And then we can take the combination and remove combination size minus 1. So the end of it. And I believe this should be it. Oh. Ooh. There we go. This occurs in O of, I don't even know what this occurs in. My guess, if I were to guess, 2n, 2n. Yep. This probably isn't the best use of my time. Graphs is probably a little better. Okay, so what I will do here is I'm going to iterate through all of the, I'm going to iterate through each single tile in the grid. And when I encounter a piece that is a 1, I will increment a counter for the number of islands and then delete that island using depth first search. And then I will continue doing that. So I'm going to iterate through the grid. So for int I equals 0, grid dot length, or shoot, for int I equals 0, I has to be less than grid dot length I plus plus. int j equals 0, j is grid 0 or I dot length j plus plus. If the current value of the grid is equal to 1, I'm going to delete the island, passing in the row, the column, and yeah, it's probably better if I do that. For int row equals 0, row has to be less than grid.length, row plus plus. For int col equals 0, column has to be less than grid row.length, col plus plus. If grid row col equals 1, then I'm going to delete the island at the row and the column, and I'm going to increment the counter once. And then I have the counter variable set to 0, and then I'm going to return the counter. Yeah, so then I will write the delete island method, where you have the row, the column, and the grid. And if the row is less than 0, I want to be able to make sure that we don't go out of the bounds of the grid. So I need to do bounds checking on the rows and the columns. I need to make sure the rows are greater than 0 and less than the length of either the row or the column of the grid. So to do that, I will check if the row is less than 0 or the column is less than 0, or if the row is greater than or equal to the grid's length, or if the column is greater than or equal to the length of the row's length. If this is the case, I'm just going to return and stop the execution. And after this, we know that we have a value that is within the bounds of the grid. If the grid's current value is a 0, this is not a part of the island, and we don't want to do anything, and we want to stop going in that direction. So we're going to return. So now, after all of this validation, we know that the current value of the grid is 1. So we're going to set it to 0, and we're going to run depth first search, which is just incrementing the row by 1, decrementing it by 1, and doing the same for the column. So I can run delete island on the row plus 1, passing the column, passing the grid. I can do it on the row minus 1, and then I can do it on the column plus 1, and I can do it on the column minus 1. And that way we're going in all 4 directions. And we'll be spreading. So if you run this, we should be good. Yep. And this will run in O of n times m, where n is the number of columns and n or rows, and m is the number of columns. We have a double loop running through, iterating through all the values, and then delete island will actually only occur n of m times. So it's really O of m, n times m plus O of n times m. Because with the combination of all these procedures, we only every cell is guaranteed to be visited at most twice and at least once. I'm pretty sure that's how it is. O of n times m. Yep, beautiful. Space complexity. There's no auxiliary. Oh, let me see. I don't think there's any extra space complexity. Let me look at the code. The recursion depth is at max O of n times m, but it's not going to be yeah, the worst case Yeah, due to the recursion stack. Okay, cool. So for max area of island, it's a very similar concept. So we will keep track of the area. And then I'm going to iterate throughout each cell in the grid. So for int row equals 0, row has to be less than grid.length, row plus plus. For int call equals 0, call has to be less than grid row dot length, call plus plus. And if the current value in the grid or row, if the current value in the cell equals 1, we will want to set area to the max between itself and the area of the current island, which we will calculate in a separate method, and then we can just return the area. To calculate the area, we will run depth first search on the row. I need to set those there for the row and the column. And we need to do the bounds check on both the row and the column to make sure that the current cell in the grid is actually something that we can visit. So if the row is less than 0 or the column is less than 0, we know that we have breached either the left side or the bottom. And if the row is greater than or equal to the length of the grid and the column is greater than or equal to the length of the grid, we will just return and suspend the execution. If the current value of the grid equals 0, we know that we are not on a portion that we're not on a cell that is a part of an island, so we're going to return as well. So after these two validation blocks, we know that the current cell that we have visited in the calculate method is currently on the grid and is a part of an island, a part of the island that it was originally called from. So what we will do is we'll set the grid to be 0, and then we're going to return 1 plus the depth first search value of each other cell. So we're going to do row plus 1, call grid, plus calculate row minus 1, call grid, plus calculate row call plus 1 grid, that is not it, plus calculate row call minus 1 grid. And this will do the same thing. Oh, this is supposed to be int. Return 0. What? Oh, or there we go. Okay. So here we can use a hash map to store each node, or store the originating node as a key, and actually let me rephrase that. We can use a hash map to store the original node as a key and the newly created node as a value, and then we can run breadth first search on the node and and rewrite, basically just duplicate the graph by breadth first searching through all the nodes and then setting the neighbors of each node, each new node. And we can use whether or not the hash map contains the new node's key as an indication of whether or not we've hit that node, so we don't, whether as an indication of whether or not we have processed that node, to be able to avoid infinite iteration. So here I'll have a hash map with a node and a node as a key and a node as a value. I'll call it a map, and I'll set it to a new hash map. And before that, if the node is null, I'm just going to return null, to avoid all the headache of doing all of this. So then we know the originating node is not null. So what I will do is I will take the map and I will put the node in it with a new node as the value with the node's current value. And then I will also make a queue to be able to topologically iterate through the array. And I will offer the node to the queue. So while the queue is not empty, I will, while the queue is not empty, I'm going to get the current node, look at all its neighbors, and then check if those neighbors exist. And if they don't, then I will add it to the map, and I will add it to the queue. And if they do, then I will add the newly created node as a neighbor of the currently iterated node. So here I'm going to take the current node, which is at the top of the queue, and I will iterate through all of its neighbors. So for each neighbor in cur.neighbors, if the map does not have the neighbor as a key, if the map does not have the neighbor as a key, I'm going to take the queue and offer the neighbor to it. And then I'm going to take the map and put in the neighbor and a new node with the neighbor's value. And then I'm going to take the current value, I'm going to take the current node and get the new node, and I'm going to look at the neighbors and add that value that I just added or that already exists, like so. Yeah, and then that should be it. If I return map.getNode, I will have the newly created node. Yeah, that's it. So this occurs in, we have to iterate through all the nodes and all of the out degree of each node. So it would be O of n, where n is the number of nodes, plus O of n plus node O of n times so O of V times E, where V is the number of nodes and E is the average amount of edges coming out of the node. There we go. Let's see. And the space complexity is O of N times, no, it's the same thing. Is V plus E? Maybe it is. Okay, I need to go sleep. Oh, I didn't realize this light.